Right. So what we did in the first part of this planning with limiting factors was to analyze a situation where there was just the one limiting factor, just the one. What happens if there are two or three or four? And what is difficult to do is to sort of, I mean, as you can imagine, how would I rank given I have a number of limiting factors? So we have to kind of go onto the computers to sort of do this. So because we don't have that sort of wealth in the exam, what you do get is a situation where there's more than one, well, there's just two. So you can then sort of try and work out, because you have two kind of unknowns, but you have to, key point is you have two limiting factors, and we have to kind of make do what is the best point in the use of those limiting factors. And that's what we're really analyzing in this second part. So let's take that through. When there's only one scarce resource, the idea in our previous lecture can be used to solve the problem. However, there are two or more resources. When there are two or more resources in short supply, which limits the organization's activities, then linear programming is required. So linear programming is a tool used to kind of identify the best use of the resources we have available. So it helps us to identify that point, and you'll see what I mean. So, because ultimately linear programming helps us to maximize contributions and, or if you like, minimize costs. So let's look at this example here. What we have here is that a company produces two products in three departments. Details shown here regarding the time required in each department and the available hours. So these are the available hours in these departments. So so first of all, we have some other restrictions. There is unlimited demand for product X, but demand for Y is limited to 600. Now, here's the issue here. In department A, they only have this number of hours available, and here they only have this number of hours available, and here they only have this number of hours available. So we're making two products that are going through three departments that have that don't have enough hours, as you can see. So the question is, how do we best make use of this time? That's kind of the situation here that we're trying to kind of analyze. So we need to kind of first of all just understand here. We see that we can make £4 on every unit of X, and we can make £8 on every unit of Y. So the options really are, I mean, just to show you what I'm really saying here is, I could choose just to make product X. If I choose to use product X, I'm going to use all this time on product X. So that would be technically 11,000 divided by 8. Now, here I could choose to, and here I'd be spending all of it on X, and here I'd be spending all of it on the time in product C on product X. So here I have like 1,000 units can be made in product C. Here we could make technically 4. So you could make 250, and when I say 2, this is the maximum that could be made. But you see, this is a process. One unit goes through department A and department C and department B and C. So if you look here, 8 here is 1, 3. Let's just call that 3. Let's just call that 1,350. So the truth is, even though department B has enough time to make 2,250 hours, it just will never get there, because so the maximum you're ever going to be able to make anyway, even if you used all the time, would be to make 1,000 units, because you're bottlenecked by department C. Department C is too slow. It needs 12 hours a unit. You only have 12,000 hours. And I'm not even doing the question yet. I'm just kind of emphasizing this issue of scarcity just to show you what we're dealing with. But anyway, so that's that. I could have made only product Y, or I can make a combination. That's the issue here. So we want to see what's best. Make only X's, make only Y's or make a combination, because that combination because it'll be about the maximization of our contribution ultimately, won't it? Right. So it says that, so let's see. So what we need to do is to kind of graph these and sort of see what this relationship looks like. So the first thing I'm going to do is that I'm just going to show you, first of all, what I'm saying here ultimately is that in Department A, I could make only units of X with my 11,000 hours and make no Y's, or I could make, I could make 10 units. I'm just going to call this equals to. You can call it equals to or less than, because I might not use all of them because of what I was saying, because you have the other departments that are slow. So definitely I'm almost sure that this is going to look like this, because Department C could only even have made 1,000 units. So I'm never going to use up all of this because Department C is slow anyway. So that's my first situation. Then I have Department B, where I could make only X, and that would be, of course, equal to or less than 9,000. Or I could make only Y's, and therefore cover. If you like, imagine I'm covering this right now, and I'm making only Y's. So technically I could make 900 Y's, or 1,350 X's, or a combination, something in the middle. Use the time to make both. If I do the same thing for Department C, I will end up with 12X plus 6Y is less than or equal to 12,000. So this is the relationship. And then what I'm trying to maximize here is I'm trying to maximize a scenario where I can sell. So either I sell only the X's, and if I sell only X's, I'll get £4 on every unit, or I make Y's and sell only Y's and get £8 on every Y. Imagine this is dormant, you can't see this. Or I sell a combination. So these are I'm almost trying to find what is the optimal point. What is the point? What is the best use of this resource, of these resources, given, what is the optimal point given the best use of these resources? That's really the issue here. So let me try and plot this graph so you can see where I'm going. You can see this says 8x plus 10 plus 10y is really what I'm trying to make happen here. Right. Oh, interesting. So this is 8x plus 10. 8x plus 10y. So this has come from, I'm just looking in your textbook to see where this question, yes, here we are. This has come from here. So where are we? So you have a scenario where, I'm just going to go to the next page. So I'm just going to put here units of X, and I'm going to put here units of Y, and kind of exactly what I was saying. Sorry, units of, this is Y, and this is X in terms of the axes. So it's what I was saying earlier on. If I choose in Department A could make only Y's, and that's what it would be, and Department X would make only X's. So if I go back a little, if I choose to make, in Department A, if I choose to make only Y's, I would make 1,100, right? I'd make none of these. I'd make only Y's, so I'd have 10Y is equal to 11,000. So that means Y is equal to 1,100. So going forward, this would be 1,100. Or if I chose only to make X's, I would have 8x is equal to 11,000, which is about 1,300 and something. Let's just say 1,375. And that would be over here, 1,375. Or I could make something in between. But at least that's the point, that's the line. You can see what's going on, right? Then let's look at the next one. So for Department X, I could choose to make only Y's again, which would be 900, or I could choose to make X's, which would be 9,000 divided by 4. So if I do that, in terms of y's, I could choose to make 900, or I could choose to make, I think it's about 2,000, maybe say 2,300, something like that. So you can see you already have issues here. The max you're going to get out of here is 900. This is totally pointless now. You're not going to get this because this product has to go through the processes, through A, through B, through C. So you have bottlenecks even within. So you can see this point is actually gone, as is this point, because this is restricted by the lack of resource of unit X. So it doesn't matter even if you have more. You're not just going to make that number of X's when it gets through that process. Okay, great. And then finally, if we go back with here, I could make 1,000. I could make 1,000 X's or 2,000 Y's, right? Because that's kind of like 12,000 divided by 6 is equal to 2,000 Y's, or 12,000 divided by 12, which is 1,000. So in terms of X's, I can make 1,000, but I can make 2,000 Y's. So you see that I now have something that looks like this. Okay, great. I haven't drawn the best of curves, but you can see here that I'm telling you that there's a point somewhere here, which at least these are units. So I'm trying to maximize my units given my restrictions. Now, just to change my pen color tells me, or my contribution curve tells me that C is equal to 4x plus 8y. So imagine if I was trying to get a contribution of 8 pounds, for example, right? Because C is equal to 4x plus, yes, that's right, C is equal to 4. Imagine I had a contribution of 8 pounds. Well, what does that mean? If I had a contribution of 8 pounds, I would get 2 units of X or 1 unit of Y. So my curve would look like this. Either I would have, like I said, 2 units of X and 1 unit of Y. This is the ratio. If I was to get, so if I had 16 pounds, I would be having 4 units of X and 2 units of Y. So basically my contribution curve is going to look like this. And what we're trying to do is we're trying to push this out to find out what's the maximum point. At what point how far can we go, because we're restricted. We're trying to make sure we can use as much of these resources. What's the highest point? And the truth is, you could always test it. Remember, these are points. You could say I'm going to make here. So therefore that's going to be this number of Y's and this number of X's. You'll see that it won't give you the maximum until you get to the furthermost point. And in this question, because please, you're using your textbook as well, this is really looking at that chapter. In this question, the furthermost point is, just because I'm running out of time as well, the furthermost point is looked at point C. Well, when I say point C in your textbook, they look at, oh sorry, then you're also restricted by, you can only sell 600 Y's. So you have something that looks like this. Something like that. But the key point is that we have two curves. Well, this time a straight line and a curve. You could have had 2 curves, and then we would have used simultaneous equations, which we've been practicing in earlier examples and earlier classes. So what we then do is, well, the 2 curves that are crossing in this scenario are 8x plus 10y is equal to 11,000, and y is equal to 600. I mean, I'll do simultaneous equations using 2 other curves just because, but this is the scenario we have. So this is the optimal point where these 2 curves meet. Well, this is a nice one because all I have to do is just plug this in here and I can find x, right? All I'll say is 8x plus, where do these lines meet? Where times 600 is equal to 11,000. So 8x plus 6,000 is equal to 11,000, and 8x is equal to 5,000, as in 11,000 minus 6,000. So if 8x is equal to 5,000, x is equal to 5,000 divided by 8. So I found x, and x being 625. I can go and plug, I mean I have y, so I have 625 and 600. So this is the point. These are the points I want to be working with, X and Y. So I can find my contribution now. So my contribution, of course, now is 4X plus 8Y. So I just literally go 4 times 625 plus 8 times 600, and you're there. And this comes to 7,300. So I'll just do another simultaneous equation one, just because time is going. This is longer than I wanted it to be. So let me just create a new sheet. If you remember, when we talk about simultaneous equations, you could have had two curves. I could find just what two of these curves could look like. I'm just going to pick two of them now. I'm just going to pick the 8x plus 10y is equal to 11,000, just for practice, and 4x plus 10y is equal to 9,000. Simultaneous equations are about trying to eliminate one of the letters. So for example, in this scenario, these two are already the same. If they weren't, I'd multiply to try and I need to make sure that the two coefficients are the same. Now these are the same, so all I'll do is subtract. I can call this equation 1, I can call this equation 2, so literally subtract equation 2 from equation 1. So what does that mean? 8 minus 4, that's 4x. 10 minus 10, that's 0, is equal to 11 minus 9,000, that's 2,000. So that means that 4x is equal to 2,000. And that means that x is equal to 2,000 over 4, and that means that this is equal to 500. So at least all this is just telling me is the points at that where they both meet. What are the x and y's where they both meet? Well, I know x is 500. I can easily find y by plugging it back in, right? So 8x plus 10y is equal to 11,000. I know what x is. X is 500, so 8 times 500, which is 4,000, plus 10y is equal to 11,000. Bring that over there, so 10y is equal to 6,000, and that means that y is equal to 600. So I mean, well, we were told that was the maximum anyway. So the key point is that we can play around with simultaneous equations anyway. So what am I saying? The key point here is that what you want to be able to do is that we want to it's been a bit long. Your targets, your aim is to, first of all, create those equations create the equations so you understand what your constraints are. And then plot your constraints, or if you like, draw the picture. You'll probably be given the picture. You'll probably be told the maximum point, also the optimal point. And then you have to use probably some kind of simultaneous equations to solve that. And then plug those x and y figures into the contribution equation, and you will then have your contribution for that x and for that y. Okay, just some final theory to go through. Typically, we're assuming we're trying to maximize contribution. We might be trying to maximize contribution whilst minimizing risk. So we haven't quite analyzed risk when doing this. We're just looking at contribution. And we also talk about this imbalance. We say each product always uses the same quantity of scarce resource. So it's this sort of normal, regular use in the same combination that we assume. So again, it is a short-term issue, really. We are ignoring fixed costs, and the fact is we're arguing the products are independent. Cool, great stuff. So I'll stop there and I'll make a final video on shadow pricing and Slack.